Okay, here we go. So if we look all the way to the question that they're asking, they want us to minimize the cost. And whenever they're asking us to minimize or maximize something, unless we know calculus, we're thinking this is probably either a parabola or linear programming, because that's the only thing we know how to minimize or maximize without calculus. So this is linear programming. So we need to set up a system of constraints here. And let's label some variables. I'm going to let t be the number of television minutes, and r be the number of radio minutes. And I'm going to set up my constraints, because if I could, I would just have, a billion hours of TV and a billion hours of radio, and it'd be just all me all the time, and it'd be good. But it's not like that. You gotta have some constraints. Every time you're dealing with real things, you have to have a positive number of minutes, so t is greater than or equal to 0, and r is greater than or equal to 0, which puts us in the first quadrant. And the first sentence says he wants at least 80 minutes and at most 120 minutes of total ad time. So the TV minutes plus the radio minutes has to be at least, so greater than or equal to 80. At least 80 minutes, but the total ad time, the television plus the radio, is at most 120. So t plus r is less than or equal to 120. So now we get into this crud. Research shows that 50,000 listeners are reached per minute when advertising on TV, and 10,000 listeners are reached per minute with radio. And he wants to reach at least that big number of listeners. So if I'm reaching 50,000 times the number of minutes for TV, so this is the number of people I reach through TV, and then 10,000 every minute for radio, so that's how many I reach per radio. I want this to be at least, so greater than or equal to 1,500,000 listeners. Yay. So those are all my constraints. I want to clean this bottom one up a bit. I'm just going to divide the whole thing. If I divide every single piece by 10,000, I'll get that this is just 5t plus r is greater than or equal to 150, and that's much nicer to look at. So now I want to graph all this. This is going to put me in my first quadrant. This will be my first line, my second line, and my third line. So I'm going to graph them over here. I've got a nice whiteboard. I still can't draw nice lines. All right, so that and that. And I'm going to go, looks like I go by 20s, so 20, 40, 60, 80, 100, 120, 140, 160, 180, and then 20, 40, 60, 80, 100, 120, 140, 160, 180. So when I graph this first line, a nice way to graph it is with intercepts. So, this is television and this is radio, we'll say. So if r is 0, then t is 80. So I've got that intercept there. And if t is 0, then r is 80. So I'll have that intercept there. And if I just connect the dots, I will have line 1. And I want to be greater than or equal to this line. So I'll make little arrows to remind me I'm above that line. Do the same thing for 2. If r is 0, just kind of block that guy out. T will be 120. So I've got that intercept there. If t is 0, just cover him up. R will be 120. And if all I need are 2 points to determine that line, connect those dots. There's line 2. I'm less than or equal to that line. so I'm beneath him. This guy here, do the same thing. If we block out R, we have 5t equaling 150. So if I divide by 5, I get that t is 30. So between there and there. And then if I block out t, if t is 0, then R is 150. So I'm there. Just need 2 points to determine that line. Whoa, totally straight line there. That's line 3. And I'm above line 3. So where all of those points, things are shaded, I'm looking at that region there. So anything shaded here fits all of those constraints. I could have, 80 TV minutes and 20 radio minutes, or I could have 60 TV minutes and 50 radio minutes. Anything in that shaded region will work. But in order to maximize minimize my cost, if I want to minimize an equation that's linear, to get an extreme value, I'm going to take the extreme values of this region. So I'm going to look, they call it these the vertices of the feasible region. I'm going to need to find out what these are. So I can tell, some of them I can read really easily off my graph. Like I know that guy is 80, 0. I know this guy is 120, 0. But I don't know what those are. My graph is not perfect. I can't read these off my graph. Maybe if you graphed it super nice you could, but we're going to find these just through algebra. If I want to find that intersection point, that guy there is the intersection of line 1 and line 3. So if I want to find the intersection of line 1 and line 3, 2 equations, 2 unknowns, you're just going to solve them. So if I just take equation 1 and subtract equation 3, so I'm just going to run a negative through that. So I just change all the signs. And if I add those, I get negative 4t, the r's go away like I planned, equals negative 70. And this is so mean, t is 70/4, so 35 halves. Let me check that, make sure I'm good. 35 halves, yep, which is about 17.5 radio minutes. And if I want to know what R is, I can just plug that back in. So if I plug it back into the first one, t plus 17.5 equals 80. So t will be, if I just subtract, that gives me 62.5. So that means that this little intersection point here, the intersection of 1 and 3, is 17.5 for the x and 62.5 for the y. And you can tell my graph is a little bit off because it looks, yeah, graph is just a little bit off, but didn't have a ruler, so hopefully yours is a little bit better. Next we have to find that intersection. So that's the intersection between line 2 and 3. So I'm going to do the same thing. I'm just going to have line 2, keep that the same. And I'm going to subtract line 3. So minus 5t minus r equals minus 150. So I get minus 4t. Those go away like I planned. Equals minus 30. And t is a nasty 34ths. So 15 halves. So 7.5. So I've got t. Plug that back in to find r. So plugging it back into the first one, 7.5 plus r is 120. So r will be 112.5. So that means that this point of intersection, t was 7.5 and r was 112.5. So now we have all the vertices of our feasible region. We just have to test which one of these gives us the minimum cost. So my cost function is given by, says it costs, cost of advertising on television is $800 per minute. So 800 times the number of minutes for TV. And then radio is 200 per minute. So I have to add $200 for every minute of radio. And so one of these, just plugging and chugging them in, is going to give me a minimum cost. So I'm just going to set up a table with all of those points. So 80, 0, 120, 0, 17.5, 62.5, and 7.5, 112.5. Plug them into here. So this was T and this was R. So 800 times 80 plus 200 times 0. That gives you 64,000. And 800 times 120 plus 200 times 0 gives you 96,000. And 800 times 17.5 plus 200 times 62.5. That gives you 26,500. And 800 times 7.5 plus 200 times 112.5. That gives you $28,500. So we're looking for the minimum cost. So the smallest one here is that one. So our final answer, almost there, is that we get a minimum cost of $26,500 when we have 17.5 minutes of TV and 62.5 minutes of radio. So we're going to say minimum cost of $26,500. We use 17.5 minutes of TV ads and 62.5 minutes of radio. Phew! That is all.